Okay, so let's try a little thought experiment. Imagine you had to draw a perfect map of the 5G signal inside a huge skyscraper. But here's the catch. You can't go inside. Sounds impossible, right? Like something out of a sci-fi movie? Well, it's a very real problem, and it's one that researchers are now cracking with a really fascinating new AI.
So let's start with a problem that I know you've experienced. You walk into a big building, you get in the elevator, you head up to the 30th floor, and bam, your phone has 1 bar. You're smack in the middle of a dense city, surrounded by cell towers, and yet you can barely even get an email to load. What is going on?
And look, this isn't just some minor annoyance. A staggering 80% of all our mobile data traffic happens indoors. So if the signal can't get inside these buildings properly, our super-connected world pretty much grinds to a halt. For the people who plan our wireless networks, this is a massive, massive headache.
So, what is actually stopping the signal? Well, it turns out the very materials that make our modern buildings so strong and energy efficient are also building these invisible fortresses against our 5G signals.
Yep, these are the culprits right here. You've got things like reinforced concrete, special metallic insulation, even some kinds of multi-layer glass. They're all fantastic at blocking radio waves. We're talking about a signal loss of 20 to 45 decibels. Now that might just sound like a number, but trust me, that is more than enough to take your connection from 5 bars of glory down to, well, basically nothing.
To fix this, what network planners really need is a map of the signal inside the building. Now, the old way of doing this, literally sending people floor by floor with scanners, is just way too slow, it's expensive, and it's a huge pain. A much cooler idea is to use drones, but there's a huge catch.
And here it is. This is the core dilemma. Drones are fantastic, right? They can fly all around the outside of a building, gathering just tons and tons of data about the signal strength out there. But they can't exactly phase through walls to see what's happening on the inside. They're stuck on the wrong side of the problem.
So this all boils down to one almost impossible-sounding question that researchers at the University of Technology, Sydney decided to tackle. How in the world do you map an invisible field through what is essentially an impenetrable barrier using only data from the outside? The answer, it turns out, requires you to think about the problem in a completely different way. And this is where a brand new AI called SpiderGNN enters the picture. The way it gets around these physical walls is by challenging a really basic, common-sense assumption that we all make about how signals work. You know, our basic intuition tells us that if 2 spots are physically close to each other, they should have about the same signal strength. But SpiderGNN knows the reality inside a complex building is way more complicated. You could have 2 offices side by side that have wildly different signals because of a thick concrete wall between them. At the same time, a spot on the 10th floor might have a signal that's almost identical to one on the 12th because they both share a clear path through a big glass atrium. It's the path that matters, not the distance.
Now, the fancy term for this is non-Euclidean propagation. But all it really means is that the signal doesn't travel in a nice, neat, straight line. It has to navigate this invisible maze of obstacles. So for an AI to solve this, it doesn't need to know about physical distance. It needs to learn the rules of the maze.
So how does this thing actually do it? How does it learn this invisible maze from the outside in? Well, it's a pretty clever 3-step process.
Okay, so here's the big picture of how the whole system works. Over on the left, you've got the drone flying around, scooping up all that raw signal data from the outside. That data gets fed into the AI, which then does its magic. It builds this really smart map, what they call a graph. It analyzes the relationships on that map, and then, on the right, it spits out these 2 incredibly precise predictions about what the signal is like inside.
All right, so let's dig into these 3 stages one by one. First, that dynamic graph construction, which is where the AI builds its special map. Second, the topology-aware encoding, where it learns from that map. And third, the dual predictions, where it gives us the final answer. Okay, this first part, this is the secret sauce. Instead of just making a map that connects points that are physically close, this dynamic graph block creates something more like a social network for signals. It looks at all the detailed features of the signal at each point and connects the ones that are behaving similarly, even if they're on opposite sides of the building. It's basically guessing that they might share the same path through that invisible maze. Okay, next up, after learning the maze, the AI makes 2 separate predictions. The first one is for RSSI, that's basically the raw signal strength. You can think of it as how loud the signal is. But the second and much trickier prediction is for CQI, or signal quality.
That's about how clear the signal is. It's the difference between a loud, staticky radio station and a quieter but crystal clear one. They're two different problems, and they need their own specialized parts of the AI to solve them.
So the theory sounds absolutely incredible, but does this thing actually work in the real world? Come on, let's look at the results.
First, let's see what the competition looks like. This was a previous state-of-the-art model. And if you look at these charts, you can see the predictions. I mean, they're in the right ballpark, but see how the dots are kind of scattered all over the place? Especially for signal quality, the CQI on the right, it's a total mess.
But remember, SpiderGNN doesn't just connect the dots based on where they are. It thinks differently. It learns the building's own secret language. And here it is, the wow moment. Just look at that. Look at SpiderGNN's charts. It's not a scatter plot anymore. It's a straight line. The predicted values are lining up almost perfectly with the actual real-world measurements. This AI is seeing inside the building with absolutely stunning accuracy, all from the outside.
Now, the numbers here are they're ridiculous. We're looking at a metric called R-squared. Just think of it like a test score, where 1.0 is a perfect 100%. For signal quality, that really tricky one, the old model scored a 0.6. Not great. SpiderGNN, a 0.9949. That's basically a perfect score. It represents an error reduction of up to 89%. That is a gigantic leap forward.
And I think this quote from the researcher's paper just sums it all up beautifully. They say, the result is not merely a better graph, it is a more honest one. What they mean is, SpiderGNN isn't just a clever algorithm. It's successful because it actually respects the real-world physics of how these signals behave, creating a model that's more true to life.
So what does all this mean for you and me? It means we now have a fast, cheap, and totally non-intrusive way to map out indoor wireless coverage. This could completely change how we design and build the 5G and eventually 6G networks that our future cities are going to rely on.
Now, to really get why this is such a game changer, you have to know this number. Over 80%, 80, of all our mobile data traffic happens inside buildings. I mean, just think about it. You're at work, you're at home, you're in a coffee shop. We're almost always indoors when we're glued to our phones.
And that brings us to this huge paradox, right? If we spend all our time using our devices indoors, why are the very buildings we live and work in so incredibly good at blocking the signals we rely on?
This problem gets really obvious in what you could call the high-rise dead zone. As our cities build taller and taller, our cellular signals just can't keep up.
So let's meet the usual suspects. The materials that make our buildings so modern and energy efficient. Things like reinforced concrete, metallic insulation, even those fancy multi-layer glass windows. They are absolute killers for radio signals. We're talking a signal loss of 20 to 45 decibels. That's easily the difference between a perfect 5G connection and, well, nothing. And for us, the result is that feeling we all know way too well. The dropped calls during an important conversation, the video that just buffers and buffers, that frustrating feeling of being totally disconnected even when you're in the middle of a bustling city. So, engineers had a pretty clever idea. Why not use drones? They're fast, they're cheap, and they can fly all around a building to measure signals. But this smart idea came with its own big problem.
So you can use a drone to scan the entire outside of a skyscraper, collecting just a massive amount of data on the radio frequencies. You end up with this beautiful, detailed 3D map of the signal environment. But, and this is a big but, it's only for the outside.
And that led them to the million-dollar question. And I'm pulling this right from their research. You've got this perfect map of the outside world, but how in the world do you use it to see the unobservable world on the inside? A drone can't fly through walls, so how do you make that jump?
This is where the real breakthrough comes in. A new AI framework called SpiderGNN was created to solve this exact problem. And the trick is, it doesn't think like a person. It actually tries to think like a radio wave.
Here's the core innovation. See, older methods just assumed that if 2 points are close to each other, their signals should be similar. But that logic completely falls apart the second there's a concrete wall between them. SpiderGNN, it just ignores physical distance. Instead, it builds this web, connecting points based on how their signals actually behave, no matter how far apart they are.
The whole process is actually really elegant. It's kind of 3 simple steps. First, it builds that custom signal web we just talked about. Second, it watches how signals travel through that web to really understand the building's unique layout. And finally, it makes 2 separate, super accurate predictions about the signal inside.
So let's zoom in on step 1. The model doesn't just use some generic map. No, for every single building, it looks at the fresh drone data and builds a brand new spider web from scratch. This web becomes a unique signal fingerprint, tailored perfectly to that one building's materials and design.
Okay, so once that custom web is built, the model sends information flowing across all those connections. This is how the AI learns exactly how radio waves are bending, bouncing, and penetrating that specific structure. It creates a complete, holistic picture of the signal landscape inside. And this last step is just so clever. Instead of making one generic prediction, the model splits into two. One branch predicts signal strength, that's basically your bars. The other predicts signal quality, which is, is that signal actually good enough for a fast download? Because strength and quality aren't the same thing, predicting them separately makes the final result way more accurate. So that's the theory behind it all. But the big question is, does it actually work in the real world? Well, the answer is a resounding yes. The results are frankly stunning.
I mean, just look at this. On the left, you've got predictions from a pretty standard AI model. See how the dots are all over the place? It kind of gets the general trend, but it's really messy. Now look at the right. That's SpiderGNN. The predictions are incredibly tight, lining up almost perfectly with the real-world measurements. And the actual numbers are even more mind-blowing. Let's look at the R-squared score, which is just a measure of accuracy. A 1.0 would be a perfect score. For signal strength, SpiderGNN gets to a near-perfect 0.99. But check out the really hard one, signal quality. The baseline model is meh, 0.6. SpiderGNN leaps to an incredible 0.99. That is a truly game-changing improvement.
What a score over 0.99 really means is that this isn't just a good guess. It is a startlingly accurate reconstruction of the indoor signal environment, all created from one simple drone flight on the outside.
Now, this level of accuracy isn't just a cool academic exercise. This has huge, profound implications for how we actually plan and build our wireless networks. It's like we've been given a whole new set of blueprints for a better 5G future. And the researchers themselves really lean into this practical side. Think about it. Instead of sending teams of engineers on slow, expensive, and disruptive walkthroughs of every single floor of a skyscraper, network providers can now get a richer, more detailed 3D signal map from one quick drone flight.
And this is really the key takeaway. For decades, there's been this massive gap between what we can easily measure outside a building and what we desperately need to know on the inside. SpiderGNN finally bridges that gap. It solves what the paper calls a persistent challenge for anyone trying to plan wireless networks in our modern vertical cities.
And the team isn't finished. The next steps are all about making this system even more powerful. We're talking about adding support for new, higher frequency bands like M-Wave, predicting other critical things like network latency, and even getting to a point where the drones are smart enough to plan their own flight paths to get the best data.
But first, let's talk about something we've all felt. You know the feeling, right? You've got that blazing fast 5G connection, you walk into a building and bam, it just slows to a crawl. So why does our most advanced wireless tech still get beaten by a simple concrete wall? And this is a huge deal because, get this, a staggering 80% of all our mobile data traffic actually happens inside buildings. So solving this indoor coverage problem, it's one of the most important challenges for our super connected world. The fundamental issue has always been this. To fix the signal inside, you first have to know where it's weak. And that usually meant someone had to physically walk through every single floor with special gear. As you can imagine, that's slow, it's expensive, and it just doesn't work for, say, an entire city. The holy grail has always been to figure out that indoor signal map without ever going inside. So how do you even begin to solve a problem like that? Well, a team of researchers came up with an absolutely brilliant solution called SpiderGNN. And honestly, the name is perfect because it weaves together a complete picture from these scattered invisible threads of data. The whole concept is actually really elegant. You take a drone, equip it with some RF scanners, and fly it around the outside of a building. It just picks up these little bits and pieces of signal data that leak out. Then, and this is the magic part, a powerful AI takes that limited external data and builds a complete, detailed 3D map of the signal quality on every single floor inside. So here's a quick look at how it all works. The drone is kind of like the scout, flying around and scanning the building. The AI, which is a special type called a graph neural network, is the brain. And what makes it so smart is that it doesn't just look at individual data points. Nope. It's designed to understand the hidden relationships between them, building this dynamic signal web to figure out what's really happening inside.
Now, to really get what the AI is predicting, you gotta think about your phone's signal in two different ways. It's not just about how loud the signal is, it's also about how clear it is. Let's just call it volume versus clarity.
And these two ideas right here, they are the stars of the show. On one side, we have RSSI, which is the raw signal volume. On the other side, we have CQI, which represents its clarity. Being able to predict both of these is absolutely the key to understanding what a user is actually experiencing inside. Okay, let's start with RSSI. This is just the raw power your phone is getting from the cell tower. So, using a radio analogy, think of it as the total volume you hear from your speakers. It's got the music you want, sure, but it also includes all the static and interference. It's just a measure of pure energy. CQI, though, is way smarter. It measures the signal's quality, its clarity. It's what tells the network how good the connection is so it can adapt on the fly. In our radio analogy, this is like the DJ noticing there's a bunch of static and deciding to speak a little slower and clearer so you can actually understand what they're saying. Because, let's be real, high volume doesn't mean a thing if you can't make out the words. But SpiderGNN doesn't just stop at volume and clarity. To build a map that's truly useful for future networks, like 6G, it also captures a few other really critical details. These add even more layers to our little radio story. So let's run through these real quick. First up is RSRP. This measures the pure signal from just one tower. Think of it as the volume of only the DJ's voice. Then you've got SNR, the signal-to-noise ratio. This compares the DJ's voice to the static. You know, how much louder is the good stuff than all the junk? And finally, there's RSRQ, which measures the overall quality by comparing that useful signal to all the other noise and interference combined. All right, so the theory is just beautiful, right? You've got drones, you've got AI, you have this deep understanding of all these signal metrics. But does it actually work in the real world? Well, the data speaks for itself, and honestly, the results are nothing short of stunning. This image right here tells the entire story. On the left, you're seeing predictions from the old way of doing things. See how scattered those dots are in the bottom charts? That's a loose, really inaccurate prediction. Now, look at the right side. Those are SpiderGNN's predictions. The data points just snap into an almost perfectly straight line. This is a massive leap in accuracy, where what was predicted almost perfectly matches what was really measured. Let's put some numbers on that. When you look at the prediction error for the signal volume, that's RSSI, lower is always better. The old methods were sitting at an error rate of about 3.3. SpiderGNN crushed that, bringing it all the way down below 0.8. So what does that actually translate to? For predicting the raw signal strength, SpiderGNN reduced the error by 76%. That's not just better, that's a whole new ballgame. But remember clarity? For predicting CQI, which you could argue matters even more for your actual download speeds, the results were even more incredible. SpiderGNN slashed the prediction error by a jaw-dropping 89%. And for anyone who works with data, this is the mic drop moment. The model hit an R-squared value of over 0.99. What that means in plain English is that its predictions explained more than 99% of what was happening in the real world. I mean, that's about as close to a perfect crystal ball as you can possibly get. So what does this all mean when you put it together? This isn't just a cool science project. This technology fundamentally changes how we can design and manage the wireless networks that, let's face it, our whole society is built on now. This quote from the researchers just sums it all up so perfectly. By capturing all these different layers of the signal, the volume, the clarity, the noise, you don't just get a better map of the inside of a building. You get a more honest one that truly reflects what a person using their phone will actually experience. So the big takeaway here is really clear. For the very first time, we have a way to quickly, cheaply, and super accurately map the invisible world of indoor signals, without all the crazy expensive and disruptive manual testing. This lets network operators pinpoint weak spots with surgical precision, making sure our hospitals, our offices, and our homes have the rock-solid connectivity they absolutely need. And that kind of leaves us with one last really fascinating thought. We've just figured out how to turn invisible radio waves into a detailed, predictable map. It really makes you wonder, what other crucial, invisible forces that shape our world could we make visible next?